And the first talk is given by Oliver, and he's from Wisconsin Medicine. And his talk is about the flow imaging of the thoracic aorta technical view. Please.
Thank you for the kind introduction. Good morning, everyone. It's my pleasure to speak to you about the technical views and implications of scan parameter choices for flow imaging of the thoracic aorta, specifically 4D flow imaging. I want to disclose that I will be serving as the incoming president here of the SMRA, and my institution receives research support by GE Healthcare. 4D flow imaging is very rich in the information it can provide. That is true for vascular anatomy as well as for 3D velocity fields from which secondary hemodynamic parameters can be derived. That includes things like simple and straightforward flow measurements, visualization of complex flow patterns, and hemodynamic parameters such as vorticity, helicity, wall shear stress, or pressure gradients. That's why it makes it 4D flow very appealing for the assessment of various conditions of thoracic aortic pathology. So I borrowed a slide from a colleague of mine from Tekla Öktering, who has identified some of the main applications as she sees it for 4D flow MRI. I'm not going to review it. I just want to make the case that there's plenty of interest for hemodynamic assessment of the aorta from a clinical perspective, and you will hear much more details about that from our next speaker, Dr. Itatani. I structured my talk to follow the work pipeline of 4D flow imaging. So I'll start with data acquisition and reconstruction, which go hand in hand. I will then talk about what we often call pre-processing data corrections, and then finish up with post-processing and visualization. And again, the focus is on the technical aspects of that. So let's kick things off with data acquisition and reconstruction. I'm showing you here what I call the workhorse of the 4D flow sequences. I believe this is by far the most used sequence. It's kind of adapted from the Michael Markle sequence. It's a segmented case-based acquisition, Cartesian sampling, uses what we call 4-point encoding, so 3 velocity encodes and a baseline, and there are different ways to encode those 4 different points. They are typically respiratory gated, so there's a loss in efficiency and an increase in scan time because of that. It's usually a window somewhere in the 40–50% range. We use ECG gating, either prospective or retrospective, and without any additional modification, this leads to very long scan times. Relatively typical set of scan parameters shown on the bottom: spatial resolution, in plane 2 by 2 millimeters, slice thickness of 4 millimeters. We target usually temporal resolution in the 40–50 millisecond range, and that leads to scan times in the order of 12 to 14 minutes. Again, those are just some representative values. Everybody has their own little modification of that. And with such acquisition, we can get beautiful images. Again, those are acquired with such a sequence here from Dr. Markle. We have nice coverage of the aorta. We have in detail information about the velocity vector fields, and presents kind of a view that is not accessible through any other medical imaging modality. There's no ultrasound or CT scan that can generate such rich data sets. I would say that I feel pretty comfortable to say that the aorta is probably the most targeted 4D flow acquisition if you look at the literature or so. And there are several reasons for that as I see it. One is that the requirements to do a successful scan are relatively modest compared to other vascular territories. The aorta is the largest vessel in the body, so we can get away with larger voxel sizes. And there's also, on top of that, high clinical interest and high research interest, as I will show in some of the next slides. So perfect scenario to use 4D flow for aortic imaging. I want to talk about some of the consideration for the data acquisition. So we're obviously, with these long scan times exceeding 10 minutes, we have to use free breathing type of acquisitions. There's substantial motion of the diaphragm, obviously, through the respiratory cycle, but not only the diaphragm. You see on the movies the motion in the SI direction, but also in the anterior-posterior direction. And if you look carefully, you can see that the aorta, for example, the root region, is affected by this. It turns out that some acquisitions with 4D flow are actually conducted still with ungated acquisition schemes, because that means you're not having to throw away or discarding half of the data during your scan time. That obviously leads to the potential for residual motion, as I just shown in these movies. More commonly, we're using respiratory gated acquisitions. Probably the most common approach there again is the navigators, but there are other alternatives. Some groups, including ours, often uses bellows, so that's like a stretch band around the abdomen, or now we've seen definitely investigation into self-gating, which once that is really robust and good, will be really a step forward over navigators. I'd like to point you to two consensus papers from the SCMR. They were written in 2015 and very recently an update in 2023 for two reasons. One, I think that's one of the strengths of the SCMR. They really have an eye on the impact or guidelines for clinical decision making or protocols, and I think they've done a good job in that space. But in respect to the slide that I just showed, in that statement, they're still leaving the door open in recommendations to acquire acquisitions without respiratory gating. So quoting verbatim here, it is also worth noting that 40-flow CMR without respiratory gating has demonstrated reasonably accurate intracardiac and vascular flow quantification in the chest with reduced scan times. In addition to the respiratory cycle, we obviously have to deal with the cardiac cycle. All our acquisitions are ECG gated, so there's cardiac pulsatility that we're interested in. We want to look at the flow differences in systole and diastole, but there are also implications of the location of the scan plane. So showing you some movies here on the right side. I don't know the Japanese signs to do the pointer. I just described the grayscale movies here in the center and on the upper right, showing you, those are not 40 flow images, but they show you cine views of the aortic root, and they show the substantial motion that this region is undergoing during the beating of the heart. And you can also appreciate the motion if you look at the axial view on the left that's color-coded for the ascending and descending aorta. The ascending aorta moves significantly throughout the cardiac cycle. This is a breath-held acquisition, whereas the descending aorta is pretty stable. So it depends where you are in the aorta, how much motion the vessel is experiencing. We'll go over this slide very quickly. There have been pretty dramatic gains over the last 2 decades in hardware advances. That comes down to much faster gradients that allowed us things like balanced SFP imaging, reducing artifacts. It's very beneficial in many ways for velocity-encoded imaging too, like intravoxel dephasing, displacement artifacts are decreased, but it can also increase uncompensated eddy currents and background phase, which is something that still plagues us a little bit in flow imaging. And then the availability of phased array receiver coils that can be used for improved signal to noise and for accelerated imaging with parallel imaging or other kind of approaches. I would say, as I see it, that these hardware gains have to somewhat tapered off. We've reached very high performance with the gradients. I see like special brain scanners or so where we can still push the envelope a little further, but otherwise we've kind of gained some of the physiological thresholds. There is a vast array of PhD theses written in the space of accelerated imaging, and that's true not only for phase contrast or flow imaging, but for MR imaging in general. I'm listing a lot of them here that are used and have found its application in 40 flow imaging. I'm not going to go in detail through all of them, but some of the big ones are obviously parallel imaging, accelerated acquisition with constrained reconstructions, like compressed sensing, KT acceleration, and also non-Cartesian trajectories. Again, I'm not going through detail, but I want to show some of the reduction factors that can be achieved. This is an implementation from Sebastian Kozerke and Daniel Giese, he's actually here at the conference. Pretty dramatic improvements in scan time, but you have to be careful with the algorithms you're using. You might not capture, for example, systolic velocities and flow accurately if you're not using well-tuned algorithms. Something that we use at the UW a lot is radial undersampling. This is a 3D implementation here that we call VIPER for vastly undersampled isotropic projection reconstruction. We also call it the Cush ball trajectory because it kind of resembles a toy Cush ball, and it was pursued for contrast-enhanced angiography originally by Chuck Mistretta, who attended this meeting very regularly until last year. And he has now retired from his scientific career. This was adapted in the 2000s to flow-sensitive imaging with the use of bipolar gradients, same principles, and it turns out that it's very well suited for undersampling, those kind of acquisition. We used it as a replacement for contrast-enhanced MRI. Of course, you can also use contrast agent, as we often do with 4D flow imaging. It's a longer slide here, but there are several significant advantages of this approach as I see it. You can really accelerate the acquisition by preserving high spatial resolution and large coverage. You can get high-quality angiograms that has favorable motion artifacts, and it enables pretty sophisticated retrospective gating, both for the respiratory and the cardiac cycle. This has been adapted by also for 5D flow processing, where we kind of double gate to both of these acquisitions. You've seen a couple of slides here at this conference. Some of the drawbacks are longer reconstruction times and higher demands on the computational efforts on the reconstruction engine, and also more sensitivity to artifacts from trajectory errors and off-resonance. But these kind of methods that I've shown, they've really led to dramatic reductions in scan time. The first 4D flow paper was in the range of 29 minutes for an acquisition, and we're now down to 10 minutes and less for many of the acquisitions. Let's talk about the next step, data corrections. That turns out there's a lot to do in phase contrast imaging, but the good news is it's pretty well understood. A lot of these errors can be proactively calculated during the reconstruction or during some of the simple pre-processing steps like background phase corrections. There are a couple of good papers that review those kind of settings. I'm listing a couple here. Also the consensus papers that I listed earlier are a good resource for that. So last part, processing and visualization. We're in a really good space now that there are quite a few post-processing packages available, both for clinical work that are approved by authorities like the FDA, for research applications, and also tools that are shared as freeware packages. There are, I think, 2 or 3 vendors displaying their 4D flow package here at our conference, so go and check them out. So if I would have given this talk 6, 7 years ago, there would have been very little on this slide. There's something to consider, and that study was already cited by Susanne Schnell yesterday in one of the future talks, is that there are some discrepancies with analysis packages. If you use the same data with different 4D flow packages, you will not always get the same results. I think it often has to do with the segmentation engine, but it's an area that we like to see more consistency down the road. In my intro slides, I mentioned that 4D flow is very rich in kind of the hemodynamic parameters that can be derived from the velocity fields. I'm showing you a few here: pressure gradients, shear stress, pulse wave velocity, turbulent kinetic energy. And I'm picking one wall shear stress as one example because I want to make the point that depending on what you're interested in, you might want to optimize your acquisition parameters. So wall shear stress describes the drag of blood flow on the vessel wall. It's calculated as a derivative of the velocity in a very slow flow region. The vessel wall is slow flow, and it moves a bit. So it's a challenging parameter to accurately measure. It goes back to these movies that I showed you earlier. If you're calculating a derivative with a low VNR in the wall area, that will affect your measurement. So this might be an acquisition where you want to use a very low Wenck setting. If that's all you're interested in, that might be better than capturing the peak systolic velocities. For the last 2 slides here, I want to review, or I want to point at some of the exciting new directions in post-processing. Machine learning obviously has made a big impact in the field everywhere, including 4D flow imaging. There's a very nice review article I'm pointing you here. One of the low-hanging fruits are segmentation approaches to automate those instead of having them manual or semi-automatic like we've done in the past, and automatically picking analysis plane locations. And we saw a talk earlier today how machine learning can be used to automate this in more robust and more reproducible results. There's also some exciting work combining computational fluid dynamics and 4D flow and machine learning for things like super resolution imaging or denoising. We're seeing some things that have been adapted in the brain now to 4D flow imaging, to atlas-based analysis. going to go through this really quickly. This is work from Northwestern, from Alex Barker, where they map individual wall shear stress maps from one subject to an atlas. So it accounts for anatomical variations, and then they create heat maps of regions that are of particular interest, that are either much higher or much lower in terms of wall shear stress. And they can use that for large-scale analysis. So I like this a lot. I think this will really bring the field forward. And I'm, in interest of time, skipping this to my summary slide. So I hope I showed you that there are quite a few protocols available and established for 4D flow imaging, as well as post-processing solutions. I think we still have a way to go to turn those into true validated biomarkers. We're generally out of numbers, but some of them need maybe a little bit more thoroughness, and exciting new developments with machine learning. With that, I'd like to thank you for your attention.
So is there any question from audience? We can have a short question. So maybe one very short question about the artificial intelligence in 4D flow. We have developed a lot of reconstruction algorithm based on artificial intelligence, deep learning, and also the post-processing. What's the future direction of that?
What's the future of image reconstruction algorithms?
Yeah.
Yeah. I mean, you saw my future outlook slides. They didn't mention reconstruction. I'm not sure if I see huge developments. One of the new things is 5D flow. I'm not necessarily sure it brings you much for aortic imaging. This is more something for intravascular on the venous side, where the pressures change much more, in my opinion. So yeah, I think we've seen a lot of progress in reconstruction, but maybe it's slowing down. But the machine learning part is certainly something that will find its way into 4D flow reconstruction as well.
Okay, thank you. Thank you, Oliver.
Mm-hmm.